Okay, and welcome back to BME 2315. In this lecture, we'll be talking about the general topic of regression, and in particular, we'll be focusing on linear regression. This little cartoon right here actually symbolizes a fair amount of the idea of machine learning, of which linear regression is one type. Basic idea is that there's lots of information in the cloud or all around us, and that if we can somehow shove that data into a computer, we might be able to make forecasts and analyses and interpretations of that information. So there are many different types of machine learning. Machine learning basically means developing algorithms that get smarter and smarter over time, and it can make predictions about how things work. And some of those have been in areas like reinforcement learning, where different game development has been done. There's unsupervised learning that's used in marketing to the customers and deciding what customers are more likely to buy which products. And then finally, in supervised learning, you see regression is one big type of that, and so that's what we'll be focusing on today. Some of the applications of regression include market forecasting, weather forecasting, or advertising popularity prediction. So basically areas where you want to take data that you've got now and make predictions about what may happen in the future. There are, of course, many examples of regression in biomedical engineering as well, and I'll just focus on a couple of them. One of them that was really fascinating a couple years ago, a team that coupled with Google developed algorithms that can take pictures of skin moles and make classification about how likely they are to develop skin cancer. And one of the fascinating things is this group found that they could develop algorithms that were just as accurate as dermatologists that were board certified. And so that's really kind of an amazing accomplishment. Similar sort of claims and accomplishments have been made in other areas as well. One of these is retinal imaging, where you can, by taking pictures of the eye, and make diagnoses about complications from diabetes and things like that. There are many different areas where we need to think about how we can excuse me, make algorithms that can do computing to then make predictions about people's health in the future. Okay, so with that as a motivation, let's look at how we'll dive into this. And so there are mainly two types of regression, linear regression and nonlinear regression. So today we're going to be totally focused on linear regression, and then in later lectures we'll talk about nonlinear regression a little bit. So in linear regression, the idea here is that given a number of data points, can we fit a model that we'll call F to that data, and that is not necessarily going to be a perfect model, but it would be a good enough model that allows us to do forecasting to predict what happens for other values of X that haven't been measured. And so if I write that out, we've got a model F of I equals A0 plus A1 X of I. So once you have that model, for any new input xi, you can make a new prediction f of I. And so then we're going to define an error. That's the difference between the model prediction and the actual data as that's also called the residual, because it's the amount that is not explained by the model. As so EI equals YI minus F of I. So for each output, each data point, we're going to say The difference between that and the model prediction is our error EI. And so what we're trying to do is our goal is find the best fit by minimizing the sum of squared errors. Known as SSE. Okay, so the sum of squared errors is given as SSE is a square of the errors, or given in this term right here. So how would we find the best way to minimize the sum of squared errors? Well, that's going to take a little bit of derivation, and so please hold with me for a little while. But let's first take a look at our definition for the sum of squared errors is this, where this is our data. Okay, and these are our model productions. Okay, and right now we're assuming that this is the model, and this is a linear model. Let me correct that. Okay, we've got a linear model. Okay, and so what we're going to want to do is take a look at this surface, this sum of squared errors, and it depends on both A1 and A2. A1 and A2 are the two coefficients that define our model. And so what we're going to be doing is trying to find the combination of A1 and A2 at which we have a minimized sum of squared errors. So to find that minimum, okay, we're going to want to take derivatives of this cone right here. So it depends on both A1 and A2. And we're first going to take the derivative with respect to A1. And so remember, this is the function that we're taking the derivative of up here. We get -2 yi minus A1 minus A2 xi. And we're going to set that equal to 0 in a second. And then secondly, we'll take the derivative with respect to the second variable, A2. Okay, and so that's going to look similar. Yi minus A1 minus A2 xi multiplied by xi. Okay, and so once we take those derivatives, we want to set them equal to 0, because that's where you have minima or maxima, is when derivatives are 0. So we want to find the case where, so we're going to set these to equal to 0. So we've got n a1 plus a2 sum of xi equals yi. So that's just rearranging that first equation. And second, we have a1 sum of xi plus a2 sum of xi squared equals xi yi. Okay, so that gives us two equations and two unknowns. The unknowns being a1 and a2. Okay, and if we solve for a1 and a2, we would get the following. I'll give you the derivation on the next slide, but I won't go through the whole derivation. The a2 is going to be given by n xi yi minus sum of xi sum of yi. And then sum of x's squared minus sum of xi squared. And a1 is going to be given by the average y minus a2 and the average x. That's the mean of x, and the mean of y. Okay, so this gives us two equations that would allow us to solve for the least squares error. So here's a full derivation, and I'll kind of not go over that in detail right here, except to say that as before, we started with the sum of squared errors, and then we take the derivatives with respect to a1 and with respect to a2, and then we set them equal to 0, and then rearrange to get these equations for a2 and a1. Okay, so let's take a look at how we can use this derivation to solve a problem. So say we've got the following data points, okay, and we've got 1, 2, 3, 4, 5, 6, 7 data points. So write that down, 7 data points, n equals 7 data points. Okay, and we want to set and we want to solve for the two unknowns that would give us the solution to the line that goes through this. So we got two unknowns, m equals 2 unknowns. I'm sorry, the pen is slow, and so sometimes it takes a while to refresh. Okay, and we're trying to fit this function right here, f, I'll call this f instead of y to be consistent with the previous slides. F equals a0 plus a1 xi. Okay, so these are the equations. So down here are the equations that we had given for a1 and a2. So let's just kind of fill these in. So the sum of xi's are given as 28. You calculate that. The sum of y's is 24. Sorry, this is supposed to be A2 or A1. Okay, A1. I'm sorry, I'm just changing the notation here to be consistent with what we had on the last slide. This is A1, this is an A2, and that's A2, that's A1. Okay. So getting back to this, the sum of the y's is 24. The average y equals 4. The average y is 3.429. The sum of xi and yi is 119.5. And the sum of xi squared equals 140. Okay? And so if you take those numbers and plug them into our equation for A2, we get, let's see, we had n is 7 data points. 7 times 119.5 minus 28.24 divided by 7 times 140. Minus 28 divided by 28, or times 28. Okay, and if we compute those together, we'll get 0.839. Okay, and then if we take to the second equation, we're going to plug that in, so we get 3.429 minus 0.839 times 4, which is the average x. Okay, and if we compute that, we should get something like this. So overall, we fit a function that has these values. And so now, with this function, we could plug in new x values and compute new predictions from this. Okay, so that is the first example of linear regression. In addition, there are a few other concepts that are important to know about. The first is the sum of squared errors for the horizontal line at the mean. That's sometimes used as a way of looking at how much variation is in the data set. We've already looked at our sum of squared errors residual compared to the data, as the fi is the model prediction compared to the data yi. And then finally, if you combine these two, you can calculate what's known as the coefficient of determination. And the coefficient of determination is important because it provides an overall summary statistic of what percent of the data is captured or explained by the regression line. So a perfect model would have a r squared equals 1. That would mean 100% of the data captured by the line. And a completely useless, uninformative model would have something around 0. So some of the key points for this section are that regression is used to fit models to data, usually by minimizing the sum of squared errors. And linear regression has a unique solution, just one solution, and so that's why we were able to calculate the coefficients algebraically. And finally, there are ways to quantify the regression error, such as the sum of squared errors or the coefficient of determination. So that's it for this lecture. In the next lecture, we'll be looking at an expansion or generalization of this called general linear least squares, so we can tackle even harder problems. So thanks for being here, and I hope that was useful to you.